I'm Tim Ventura from AmericanAntiGravity.com, and I'm speaking with Dr. Robert Baker, Jr., a physicist specializing in the area of high-frequency gravitational wave phenomena. Dr. Baker runs the gravwave.com website and has been following not only the work of Eugene Poglonoff, but also of Ning Li and a number of other physicists working in this area. How are you doing this morning?
Fine. I just wanted to make a comment. Although I have a graduate degree in physics, I'm basically an engineer, not a theoretician. So I look at things from a slightly more practical point of view.
Oh, absolutely. Well, that was one of the things that I took away from your website. Is it okay to call you Bob?
Yes, please do.
Oh, okay. Well, you know, I've gone through the gravwave.com website, and I was amazed by how you were able to reduce it down to, you know, a much lower number of experimental variables in terms of testing these designs. That was a big benefit, just looking through it, you know, as opposed to some of the really elegant but hard to test theories that have been floating around. You know, I'd seen a number of actual practical designs that could be built and tested easily.
Well, that's true, and I think that's one of the problems we often run into in technology and particularly in physics today, in that people look for multi-billion-dollar solutions, and somehow we've forgotten that there could be somewhat simpler ways to do things without expending that amount of time and money.
Sure, sure. Well, you just did a presentation for the U.S. government, didn't you?
Yes. This Wednesday, I was down at the Navy in San Diego in their research center and gave a little presentation on the possible generation of these high-frequency gravitational waves. Interestingly enough, the Navy has basically sponsored the rather famous experiment by Michelson and Morley that in some ways laid the groundwork for Einstein's special theory of relativity. So they, as unlikely as it might be, they are probably quite interested in this kind of a concept. And of course, its practical application to communication with submarines deeply submerged because the gravitational waves go through everything unencumbered without any absorption, so they can easily reach a submarine or, as a matter of fact, go right through the Earth.
Absolutely. Well, and it seems like the high-frequency gravitational waves behave in some ways a little bit differently than some of the experiments that the public may be more familiar with, such as the rotating superconductor, which appeared to affect kind of everything in its path, but you know, had maybe some over-unity connotations to it, at least in the way it was presented.
Well, that's true. Now, as far as the interaction of high-frequency waves with gravity is concerned, that apparently is something that is fairly accepted in the scientific community. There is a basic book by Landau and Lifshitz, two Russians. Their particular treatise on radiation fields is sort of the Bible for most theoreticians in the gravitational wave community, and they discuss, I think it's on page 396, I don't have it right in front of me, that high-frequency gravitational waves, well, first of all, the gravitational waves themselves can interact and produce what you might say is classical gravity, a Coulomb field or a kind of gravity that we're used to, but it says it's a very much of a second-order effect, but then they say except in the case of high-frequency gravitational waves where it becomes more important. My thesis has been that many of these systems, things that a friend of mine, Ning Li, that she has done and speculated on, are the change in gravity that they find, I would suggest, may be at the basis an effect of high-frequency gravitational waves. In other words, many of these things, rotating fields and high frequencies and so on and so forth, could be producing high-frequency gravitational waves that are perhaps beyond the limits of detection, their magnitudes that they generate are, but might have some influence on the gravitational field itself, and they're measuring this influence.
Oh, well, in terms of Dr. Ning Li, that was actually the reason that I had come to find your website. I've been doing follow-up research. As you may know, she disappeared from public view, at least, about going on a year and a half ago at this point. The last email that I received from her was a very brief message, but she'd indicated that she'd achieved an 11 kilowatt experimental result for gravity wave production output. I guess it was her AC gravity, which is poorly understood by myself and many others.
Well, let me comment on that a little bit. Back in May of last year, the MITRE Corporation sponsored an international forum or conference on high-frequency gravitational waves. We had about 9 participants, or participants from about 9 countries, and about 25 papers indicating quite a bit of interest, particularly in Russia and China and some of those places on this. And Ning Li gave a paper, or presented a paper there, and in that paper, which was theoretical in nature, not perhaps easily understood, particularly by the layman, she did indicate this 11 kilowatt power that theoretically could be developed by her system. AC gravity, in her mind, is simply alternating current or high frequency. Most of the rest of us consider it high frequency, but we're really talking about the same thing. That is, frequencies on the order of 100 kilocycles and on up to gigacycles and terahertz and so on and so forth.
Sure, sure. Well, I would just like to say thanks for not only putting the website up, but the work that you've been able to do, as well as, in conjunction with Ning Li and Ponklanov. I believe this field goes back to at least, I think 89 was when she published her first paper, and it's been kind of quietly developing with, periodic bouts of leaping into the limelight.
Well, she's come up with something, she together with David Torr, and this is while I think they were with the University of Alabama, came up with a very significant paper, I believe it was in 1992, and where they indicated that these gravitational waves could be refracted, essentially, that there is an index of refraction, and so one could make a gravitational wave lens out of a superconductor, in particular using a high temperature one that one could develop in the laboratory. And this, if it pans out, would lead to all kinds of optics and so forth. Would be quite an amazing feature of the studies.
Well, one of the things that I've been able to find just from reading through experimental results, as well as talking briefly to Eugene Ponklanov, has been that it looks like the superconductors that are being used, definitely by Ponklanov, but also possibly by Ning Li, are much larger than the commercially available ones in the States. Now, do you think it's possible for independent experimenters out there, just people with high voltage apparatus or induction coils who might be interested in playing around with some of these ideas, to get results using the 1 to 2 inch superconductors that are available inexpensively in the States?
Yeah, theirs go up, I think, I'm not quite sure, but almost 10 inches, certainly 10 centimeters, and they're quite large. Probably. I'll tell you, a person that, and an associate of mine in much of my work is Clive Woods at the Iowa State University. He has done quite an extensive study on various different gravity modification techniques. He, I think, would be a very good one to talk to. In fact, we were emailing each other messages today about some of the new very sensitive accelerometers, and again, interestingly, developed by the Navy down there in San Diego. And this uses MEMS technology, that is a lot of little teeny things, and they're able to sense down to a change of 1/1,000,000th of a G. These kinds of accelerometers may or may not be able to accept the high frequencies, but certainly they would open the door to some interesting studies of any devices that might possibly change the gravitational field. And I've called attention to this to Clive this morning, and he's looking into it, although he doesn't know whether the frequency response would be sufficient to detect some of these things. But in any event, this is, again, something that's not that expensive to do. As far as looking at the small ones, the YBCOs that one can get commercially, and a person can get liquid nitrogen rather easily. Any dermatologist has stores of that. Yes, there might be some work that could be done. As long as you can get an experiment that others can replicate, then you would have something. And the simpler the experiment is, and the least costly it is, the more likely one could replicate these things. So I would suggest that you and others that are listening to this might talk to Professor Woods about this and get his take on it.
Absolutely. Well, one of the things that's kind of moving me towards doing experimentation, I'm planning on doing some this summer with these technologies, is, when I first started reading about this, and I think through the majority of the 1990s, the well-known effect was the 2 to 3% possible weight loss that Ponklanov had claimed to have just from rotating the superconductors. But someone had forwarded me, and I think this is around 2001, 2002, an experiment that he'd conducted with Giovanni Modenese. And apparently,
yes,
the claim was that, they weren't getting 2 to 3%. They were able to actually knock things over in the lab with it, maybe 20, 22 pounds of force. And that was from a simple spark discharge. So,
well, that's interesting, and would be an interesting thing if they replicated. Some of the work that I saw had an interesting correlation with frequency. In other words, the higher the frequency, the greater the effect, or rather with the square of the frequency. And if you just do a little graph where you see that they were correlating with the square of the frequency, that then led me to believe, since the gravitational wave influence goes as the square of its frequency, at least on gravity as far as I know, and its generation is proportional to the square of the frequency, or the efficiency of that generation, that maybe indeed there was a high-frequency gravitational wave explanation for this. I don't understand his theory, and again, I'm not a theoretician, I'm an engineer. In this particular case, I think you have to have some experiments, and then you probably follow that up with some kind of a theory. Often you have a theory, and then you develop an experiment to develop it. But better, I think, is to develop some kind of an experiment that can be replicated, and then go from there.
Sure. Well, I know that on your website there are several proposed experiments, and I guess firstly I should ask, what your top picks might be, but then a good follow-up would be to ask, what you've been able to experiment with so far and what you're looking at for the near future.
Okay. With regard to the generation of high-frequency gravitational waves, the theory I adopt is basically Einstein's theory. He came up with the general theory in 1915, and a year later he followed that up with a determination that when you jerk something, that is, when you have a rate of change of acceleration of some mass, this produces gravitational waves, and you can use a rather complicated equation called the quadrupole equation to estimate or approximate its magnitude or power level. Okay, if you get to the jerk, then the question is how you jerk something, and it turns out the larger the jerk, that is, the larger the change in force over the shorter the length of time, and you square that, the greater the power of the gravitational wave generator is. Well, there are several ways to do this. The two top picks I have is one, a project that I'm working on with Clive Woods, where essentially you use microwave oven magnetrons, which are rather inexpensive, like $30 a piece, gang them all together, get them phase locked, which is a little bit of a problem, and have them interact with small resonators, which one has in a cell phone, and they're very inexpensive. You can get millions of them for a few $100s. Put these in a asymmetrical array on a circle, and fire them up, and in the center of that asymmetrical circle is the focus, and then you put your detector there. And Clive and I are working on this trying to emulate two stars, a double star system, and that is not only theoretically produces gravitational waves, but by the Nobel Prize winning efforts of Hulse and Taylor, they received, I believe, the Nobel Prize in 1993, and essentially proved that by watching this double star system, it was coalescing just as one would expect if it was generating gravitational waves. And this was award-winning work that really indirectly proved it. Well, in any event, what I'm trying to do in this regard is get two X-ray, tabletop X-ray lasers, separate them, have them each bang on their targets in synchronous in opposite directions, and this would emulate the centrifugal force that change in centrifugal force that generates high-frequency gravitational waves in a star system. And we could put these anywhere from a few meters apart to a few kilometers apart. The greater the distance, the more intense the radiation. This we're talking about, he has a detector there in China that would, I think, be well suited to this. With regard to what Clive Woods and I are doing, I was over at INFN in Genoa, Italy, and they have high-frequency gravitational waves detectors there, as well as Birmingham University in England. They were not, of course, developed for my experiment, or for the experiment that we might do over here. They were developed because there's a high-frequency gravitational wave background, like the microwave background. It's a relic of the Big Bang, and they have not heard anything, so to speak, from there, but their detectors would be well suited to a laboratory demonstration, a generation detection of high-frequency gravitational waves. So the detectors are there, 3 different ones, and both the work I'm doing with Clive Woods at Iowa State University and with Professor Lee at Chungking University would prove out these particular procedures.
Well, it sounds like there are really 2 paths moving forward then. One is definitely kind of, at least it appears to be moving towards the communications aspects of this technology, and then the other is the more traditional, potentially transportation-linked force beam projector. And in terms of force beams, the 11 kilowatts that I'd read about, one of the immediate questions that I'd heard from others was, how is that measured? And I guess that would be a good question to pose to yourself. What kinds of force do you think we might be able to expect from even a first-generation experimental device?
Well, it's hard to tell. I mentioned Landau and Lifshitz, but they do not give any particular specifications for the change. Now, another one that you might get in touch with is Giorgio Fontana. Professor Fontana is over in Italy, and I've met with him. He has come to some of these meetings and presented papers on gravitational wave beams and the interaction and so forth. I am not entirely sure that he has come up with the actual magnitude of the force. Now, this is one of the reasons to do an experiment, of course, is to see what goes on. But Giorgio and several others in Italy in particular are looking at gravitational wave beams and what happens when they intersect and how they might change the gravitational field. Really what they're doing, as I understand it from an engineering point of view, is that they are producing hills and valleys in what's called a space-time continuum. This is Einstein's general theory of how everything operates in the universe, and so they essentially simulate a hole, or not a hole, but a valley that you're sort of falling into, or a hill that you're falling away from over a short period of time. And this, of course, could move spacecraft, could move missiles, anywhere from bullets to ballistic missiles. It could move any kind of vehicles, almost anything you can think of. Something like that tractor beam that they had in Star Trek. So Giorgio's work, I think, is good. He reported on it earlier this year at the Albuquerque meeting of what's called STAIF, and I think that stands the International Astronautical Forum or something like that. In any event, he'd be a good one to talk about. But I really don't think anybody's actually theoretically come up with the magnitude.
Yeah. Well, one of the things that's been touched on a few different times is the difference between this approach, the high-frequency wave approach, which essentially creates peaks and troughs in the space-time continuum, in comparison to maybe more of a steady-state effect that Poggenhoff had reported early on, is that it seems like, and again, just as a personal perception, it seems like the peaks and troughs really don't violate conservation of energy. A lot of people lately have been kind of searching around for the free energy solution to all of the environmental problems and, everything caused by oil. And so one of the big questions would be, do you think that this technology would impact that free energy search at all? Or is it directly proportional to input energy?
I'm not sure, and I don't think anybody's quite sure. Again, that's why an experiment is valuable. I don't think, I've not seen any of the gravitational change experiments, and I think there have been about 3 different people that have reported on this, that have had anything permanent. Permanent would be nice because you can just come back and check it again every so often. Most of it's a very temporary change. As far as energy goes, if using either a laser or a very focused high-frequency gravitational wave, you might have some nuclear effects. And this is very speculative, and you just don't know what's going on. But you could get, in some of the work that I'm doing with the Chinese, you can get up to 10 to the 20th watts per square meter over a very, very small area. But that might have some real nuclear impacts and, might open things up. I mean, after all, when Marconi developed his ship-to-shore radio telegraphy, I don't think he ever thought about a microwave oven application of his work. So we just won't know until we actually start fooling around with it.
Absolutely. Well, and gravity is very mysterious, just in terms of not really the understanding of what it does, but where it comes from and how it relates to the other forces. I watched one of Feynman's lectures online, because the University of, I believe it's Berkeley, has been putting them up. And they're excellent video lectures, although they take a while to download. Feynman had indicated that the primary reason he'd never really pursued connecting gravity to the other forces was because on the order of particle mechanics, where you have the single particle interactions, gravity was so weak that it didn't appear to affect them. So in a way, that gap has kind of been there, and hopefully we can close that up with some of the newer research. And
going back to his work, he gave an interesting lecture on there's plenty of room at the bottom. Many years ago, it sort of signaled the beginning of the nanotechnology revolution. And so there's a lot that could be done at the very small level. And generally speaking, the higher the frequency, the smaller the thing is that either detects it or produces it. And so definitely there's a link here to nanotechnology and to some of the other things that really, what's coming up today are things that could not have been done 5 or 10 years ago. Now is sort of the time to get into this, because like tabletop X-ray lasers and some of these very, very small resonators, they just weren't around off the shelf, certainly not 5 or 10 years ago, and now they are. And the same goes for the high-temperature superconductors. We're getting further and further along there, and these, weren't as available 5 or 10 years ago as they are now.
Well, one of the questions that it kind of occurred to me, and I don't know if this is I don't know if it's appropriate to even think about yet, but once you start investigating some of the transmission properties of gravity waves, especially from a communications standpoint, do you think it's possible, even remotely, that you might pick up, well, I guess I'm not phrasing it right. I was just thinking of SETI has been looking for radio signals from the stars, from, alien races or advanced civilizations for decades now, and they haven't heard anything. And part of that is the theoretical limit attached to how fast radio waves propagate, and thus the sphere in light years that a civilization can really communicate as they evolve. But one of the things that I'd wondered was perhaps they're not using radio waves. Maybe they're using something more advanced.
Well, I would say certainly if which would you rather use? Some kind of a electromagnetic wave that can be easily damped out or absorbed by an intervening media, or would you use gravitational wave communication that essentially would have very low background noise and go through everything? Well, obviously, if there was some advanced civilization that said I was supposed to be trying to sense, you'd use high-frequency gravitational waves. There'd be no question about it. And I think basically they haven't heard anything, because I don't think if somebody was really advanced, they'd be using the electromagnetic spectrum to communicate. It just wouldn't make engineering sense.
Sure. Well, and part of that, I think, is just as our civilization evolves. 50 years ago, they were using AM frequencies to listen for ET, and now they're using spread spectrum technology, and so, sooner or later, maybe we'll reach the point where we figure out whatever they are using, if, in fact, anybody is out there trying to, call us, for lack of a better word.
Yeah.
Well, this technology is just, it has so much potential. I'm not even sure really how much ground I can cover with it. It just seems like it would affect, so many different applications that we currently have.
Well, there's something, if there is some change in polarization of a high-frequency gravitational wave, or some scattering, or, as I say, some dispersion, that is change in the phase velocity due to intervening matter, you could have essentially X-rays that could see inside buildings and see through the earth, and essentially see submarines under the water. If indeed you could get high-resolution information of building interiors, this would be a tremendous help for our war on terror, because you could see people in caves or anywhere else that they happen to be with high definition. So there are some wonderful applications here. The global positioning satellites signal, you can't get those inside mountains or in areas that are where you can't receive the signal. On the other hand, there is a anisotropic or patterned background, as I said, with this relic background from the Big Bang. That could be used as a navigational aid. You could, and this doesn't relate to the generation, but to the detections of high-frequency gravitational waves. So you could essentially find out where you were without need of a GPS signal anywhere. And I think this would be a valuable advance in our technology.
Yeah, one of the things that I've been a little bit confused about personally, and maybe you can help me answer this question. I tended to believe up until about a year and a half ago that gravity waves they propagated at the speed of light, just the Einstein theoretical limit. And there was the recent experiment with the light passing through the rings of Jupiter that seemed to support that, although I've heard some argument, as relating to, using light to measure the speed of light. But the confusion comes from a paper by Tom Van Flanderen that I've actually had linked on the website on a few occasions, where he claims that the calculations that are done for orbital velocity, and just orbital interactions, planets orbiting the sun, for instance, use an assumed instantaneous propagation speed. And he also had said it somewhere at this paper that if you plug in the 186,000 miles per second instead of an instantaneous speed, that the orbital calculations actually show the Earth falling into the sun, if I remember right.
I've read some of this material. The superluminal people, and there are several that have given papers. There's a Paul Murad with the Department of Defense that's gotten together a number of people and routinely chats over the internet on these concepts. I haven't looked at it that closely, but I think it is ingrained in the theory of special relativity that really information can't go faster than the speed of light. Now, others have talked about quantum entanglements that somehow occur in different places, and that the information from one quantum entanglement to another can, go instantly in some fashion. There's lots of work going on in this, but I'm just not, prepared, or I haven't studied enough to make a comment one way or the other.
Absolutely. Well, I've been able to track Ning Li down. I think one of the final things that I found was a funding request that apparently looks like it's been fulfilled. The Department of Defense, at least to the best of my knowledge, is currently financing her work.
Well, they did. And I was a part of the oversight committee. It was done by the U.S. Army there in the Redstone Arsenal there in Huntsville. And they did indeed have her do some research. And I was on the panel that was taking a look at that research for the Army. The problem we had there is we couldn't get a final report out of Ning. We had to get something. She is a brilliant scientist, but like so many brilliant scientists, why sometimes they're a little less than practical. And as I understand, in fact, I was on the panel and I was talking to Ning, and I said, where's the final report? Well, she just didn't quite get around to it. So that's a problem. I did talk to her about 3 or 4 months ago, and in the efforts that I'm trying to promote, she would play a role.
Oh, yeah, because the thing that I had meant to ask about actually was in terms of not just her research. I tend to focus on her because I spent so much time following up on leads, but as a case example, I guess. And then you talked about the research that you're conducting as well. You mentioned 10 years as a possible time to start seeing applications for this, at least in the scientific arena. What do you think we might be able to see in the next 5 to 6 years time frame?
It's like anything. It's a question of, really it boils down to money, which then will correlate to the amount of effort. The atomic bomb, the nuclear bomb, if it had gone along with the regular pace, probably would have taken 50 years to develop. But with the Manhattan Project and all the stops removed, why, it happened very rapidly. The same has gone on in the computer area. So it's just a question of how many resources that you want to put on it. Basically, as I see it, there is a tipping point at some time, and once that happens, then everybody will get on the bandwagon. Then I think you'll see things go fast forward. But getting to that tipping point could be within a year or two, could be within 5, maybe 10 years. It's just hard to tell when that's going to happen. If we get some funding to actually do an experiment, and we are trying to do that, then I think things would go faster, presuming the experiment will be successful. It's it's one of those things. It's going to be hard to prove whether you can. Obviously you can't prove that you've generated high-frequency gravitational waves until you get some kind of a detector that is capable of sensing them, and hopefully you'd have more than one detector. And really, you would have to have one group do the generation, another group do the detection before anybody would believe you.
Yeah, absolutely. Well, and that's one of the things that makes the force beam projector, the concept of that, a little bit more easily testable. Pogklanoff reporting that things have been knocked over. It's much easier to see the results than it is with information transmittal. But well, we're almost out of time for today. One thing that I would love to follow up on you with is just general thoughts, anything that you might have wanted to just talk about that you didn't have the time to, or just, do you have any further thoughts to leave the audience with?
Well, I think this could be a very fundamental change in our technology. Probably whoever does this, it would be similar in its effect on our society as was Marconi's experiment with radio, was the development of nuclear energy, as development of all our technology areas such as aircraft and rockets and all and that sort of thing. So this could have a very far-flung, manifest effect on society. society and how we operate, our ability to see through things, our ability to communicate, our ability to have propulsion, our ability to perhaps see other things in the universe. I don't think I can overstress the importance of this kind of research.
Yeah, definitely. The more that I learn about it, it just continues to amaze me. And one of the things, I met with Nick Cook last week briefly while he was in Washington State, and he'd also said that the amount of credibility in terms of scientific reputation that's going into this research just gives it that much more of a boost. It's real scientists doing real work, and it adds so much to it. Even in terms of just funding, that the government looks at it a lot more closely when there are PhDs involved. So, well, thanks again for your time.
Well, I enjoyed talking to you, and I hope we can do this again.
Oh, absolutely. Well, and there are many things that we could follow up on. Have a nice day.
Okay, same to you. Bye-bye.